Last set of questions about electrolysis, not specifically an A-level topic where it says let's do electrolysis now, but it pops up in many places, so it's worthwhile just going through it a little bit. First of all, we'll start with qualitative and then move to quantitative. By qualitative, of course, I mean what is formed at the electrodes when you electrolyze ionic compounds. Molten is easy. Cation goes to its element at the cathode, anion goes to its element at the anode. However, when you're working with aqueous solutions, then it's a little bit more fun. At the cathode, you're going to get reduction. You can either reduce the cation to its element, or if the cation is a particularly stable one with respect to reduction, in other words, has a very negative reduction potential, like alkali metals, alkaline earth metals, aluminium, or manganese 2, then what will happen instead is you'll reduce water, and when you reduce water, you make hydrogen and hydroxide. Same couple of possibilities at the anode. For oxidation, you either oxidize the anion to its element, or if the anion is particularly tough to oxidize, that is if it's fluoride or if it's an oxyanion that contains a high oxidation state for the other non-oxygen atom, then what will happen is you'll oxidize water instead to make oxygen and H+. So let's have a look at what we're electrolyzing right now. We have aluminium iodide. The cation is aluminium 3+. There's aluminium 3+ right there. It's very, very hard to reduce aluminium 3+. So instead, you reduce water. So thus, at the cathode, your products will be H2 and hydroxide. Now let's move to the anion consideration, the anion iodide. Where's iodide here? Well, it's not one of these tough ones. Iodide's actually relatively easy to oxidize to its element. What's the element? I2. So obviously you will therefore need at the anode balanced equation 2I- goes to I2. So at these electrodes, at the cathode, hydrogen gas and hydroxide, at the anode, iodine. Do another one, shall we? Another aqueous solution. So there's the rules for aqueous solutions that we've just gone through. What are we electrolyzing here? An aqueous solution of copper sulfate. So what's the cation? It's Cu2+. We know that because, of course, sulfate's SO4 2-. So Cu2+ is not one of these. Cu2+ is actually pretty good fun to reduce, and so therefore at the cathode we will simply reduce Cu2+ and make copper. Very, very, very common A-level experiment there, maybe even GCSE depending upon which you do it. Now what's the anion? To go with the anode, well, the anion is sulfate, SO4 2-. That is right there. It's extremely hard to oxidize sulfate because the sulfur is as high as it gets in its oxidation states, +6. So therefore, instead of oxidizing the anion, we're going to go ahead and oxidize water. When we oxidize water, of course, we make O2 and H+. So what forms at the cathodes in this one? Copper, solid copper at the cathode, and at the anode, oxygen gas and H+. Now let's move to some quantitative ideas. This is remembering that whether we're looking at equations or more probably in this case half equations, the electrons can be considered to be reactants in the reaction, and so therefore we can talk about moles of electrons. Trouble is you can't weigh out electrons in order to convert something to moles, so what you do is you convert charge to moles of electrons. 1 mole of electrons is a charge of 96,500 coulombs, otherwise known as a Faraday, and of course you don't actually have a Coulomb meter. Coulombs is charge, which is amps times time in seconds, which you measure with an ammeter and a watch. So everything we're going to do here is based around having part of the calculation involving determining the number of moles of electrons. So many grams of copper could be produced by electrolysis of a solution of copper sulfate using a current of 5 amps for 6 minutes. So the first thing we see here is that we've got 5 amps for 6 minutes. So that means we can calculate the coulombs. Coulombs is amps times seconds. Throw in everything there, and we have 1800 coulombs. Once we know the number of coulombs, we can convert that to the moles of electrons, because 1 mole of electrons has a charge of 96,500 coulombs. We only have 1800 coulombs, so our moles of electrons is 0.0187 moles of electrons. Now let's think about the actual equation we're doing, because what we're really interested in is copper. Well, here's the relationship between moles of electrons and moles of copper. So we can do that conversion quite happily. Copper 2 plus 2 electrons reversibly goes to copper. So therefore we've got 0.018 moles of electrons, but we need 2 electrons for every copper. So the moles of copper we'll make is 0.0187 divided by 2, which is 0.00933 moles of copper. And then finally, going from moles to 2 grams, something you're absolute world experts at, multiply the moles by the molar mass, which is 63.5 grams per mole, to give us 0.592 grams of copper. Piece of cake, I hope you would agree. Last question, you were given information about charge and you were asked about grams. Here we're given grams and we're effectively asked about charge because we know the amps and we're asked for the time, how long. So first thing we do when we see grams is always turn it into moles, divide by the molar mass. So we have 0.00513 moles of platinum. Now where does that platinum come from? It comes from K2PtCl4. Potassium obviously is always +1. No reason for the chloride not to be -1. So +2 -4, put all that together, the platinum has to be +2. So the equation we're going to use here is the electrolysis of Pt2+ needs 2 electrons to make the platinum. So in other words, every mole of platinum needs 2 moles of electrons. So we can determine the moles of electrons, 0.00513 moles of platinum times 2, 0.01026 moles of electrons. Once we have moles of electrons, we can get the charge, the number of coulombs, because each mole of electrons is 96,500 coulombs. Multiply 96,500 by 0.01026 moles of electrons, and we see we got 990 coulombs. Now coulombs is of course charge, or coulombs is charge, and it's current times seconds. Okay, amps times seconds. We know the coulombs, 990. We're told we have 0.15 amps, so now we can get the number of seconds. It's 6600 seconds. 40. Solution containing MnO3 twice of an unknown metal is electrolyzed. Now, we don't know what M is, but we know when we're electrolyzing it, it's M2+, because we know nitrate is 1-, so remember that. Now, let's see what we've got. We've got seconds, we've got current, so we can get coulombs, thus the charge, thus the moles of electrons, and we know the grams of the metal. So let's see how far we can get with that. Number of coulombs, amps times seconds, pop that in. So we got 148.2 coulombs. We can convert that to moles of electrons. And so we have 0.001536 moles of electrons, knowing of course that each mole has 96,500 coulombs. So we've got in 0.001536 moles of electrons. We know that the equation that we're doing is M2+, that's the M2+, we know it's 2+ because it's got 2 nitrates, requires 2 electrons to get to M. So therefore the moles of M that we're making here is the moles of electrons, 0.001536, divided by the 2 that it needs, 2 moles of electrons for every mole of M. So we got moles of M, 0.000768. So let's see what we got. We know moles of M, we know grams of M. Once we know moles and grams, we can get the molar mass, which is grams per mole, which is 103. So we know the molar mass of this metal. Look at the periodic table and we see that about 103 is the molar mass of rhodium. Not something you see very often on the A-level curriculum, but a lovely, fun element regardless. Finally, another fun little question. We've got current, we've got time, so we can get charge. If we can get charge, we can get moles of electrons. If we know what we're electrolyzing, we can get moles of nickel, and then we can continue from there. So charge, current times time, pop all that in, 39,088.5. I bet that 0.5 is really important, isn't it? Once we got that, we can get moles of electrons, which is going to be 0.405 moles. The equation, the reaction we're actually doing is nickel 2+, which needs 2 electrons to go to nickel. So we got 0.405 moles of electrons, thus we can make 0.2025 moles of nickel 2+. Now, at this point, it says what was the initial concentration of the nickel? Well, of course, concentration is equal to moles over liters. We just figured out we have 0.2025 moles of nickel, and we had 225 milliliters, or 0.225 liters, which is concentration then of 0.9 moles per liter. Hopefully those last few ones were kind of fun for you. It's just regular old stoichiometry with the little twist of having to figure out the moles of electrons from the coulombs, etc.